Hello, in this module I'm going to first show you how minimizing the average error on your training examples can actually lead to disparities in performance between groups. And then I'm going to show you a simple approach called group distribution and robust optimization that can mitigate some of these disparities. So let me begin with a very famous example of disparities or inequalities in machine learning. It's called the Gender Shades Project. In this project, the authors collected a data set of images of faces of different genders and different skin tones. And then they evaluated a gender classifier from Microsoft, Face++, and IBM. What they found was rather striking. So for a group of lighter skinned males, the classifier was almost perfect. But if you look at the performance of these classifiers on darker skinned females, you'll see that the accuracy are much, much worse. So this is a general problem in machine learning, which is that inequalities between different groups arise because machine learning is generally where you minimize the average loss. So these inequalities can have real-world consequences. So in this vivid case, a black man was wrongly arrested due to an incorrect match with another black man captured from a surveillance video. And this mistake was due to a mistake made by a facial recognition system. So given what we just saw on the Gender Shades project, we can see that lower accuracies for some groups might lead to more false arrests, which adds to already problematic inequalities that exist in our society today. So in this module, I'm going to focus on this issue of performance disparities between groups and how we might be able to mitigate them. But I also want to highlight that even if we didn't have any disparities between groups, there's a question of whether facial recognition technology should be used in law enforcement or in surveillance or anything at all. And these are big, thorny ethical questions, which we're not going to, unfortunately, be able to spend much time with in this module. But I just want to highlight that it's important to remember that sometimes the issue is not with the solution, but in the framing of the problem itself. So gender shades was an example of classification, but to make things simpler, let us consider our friend linear regression. So recall in linear regression, we start with a training set which consists of examples. Each example has an input X and output Y. But in our case, we're going to assume each example is also annotated with a group G. So we're going to have a set of, let's plot this over here. So here's 1, 4. And here's a second example, 2, 8, which is up here. And then these examples down here are going to come from group B. So we're going to have two groups, A and B, and here they are over here. Okay, so the goal of machine learning, or linear regression in particular, is to produce a predictor, such as this one. And the predictor is going to take new inputs, such as 3, and produce an output, such as 3.27. So in linear regression, we assume that the predictor has the form a weight vector dot a feature vector, phi of x. In the simple example, we're going to restrict ourselves to the case where the feature vector is simply the identity map, just x, which gives us a hypothesis class, which is the set of all lines that go through the origin. So you can think about sweeping lines through the origin here. And the weight vector is just going to be a single number, w. So already you can see some tension here. So which weight vector would you choose? Would you choose one that's closer to these points in group B or in group A? And this tension means that we have to compromise somehow. And exactly how we compromise is going to have some implications. So notice also that the predictor doesn't use the group information. It just takes an input X as before. What's going to use group information is the learning algorithm, and we'll get to that a little bit later. So just as a review, for linear regression, we define the loss function of an input xy and a particular weight vector to be simply the difference between the predicted value of that classifier, or sorry, regressor f of w, and the target value of y squared. And remember that we defined the training loss of a particular weight vector as follows. It's going to be the average, so 1 over a number of training examples over sum over training examples of the per example loss. So visually, we can see this on this plot where for each value of w, in our case here, remember w is a scalar for this particular example, we get a loss value. So this is the training loss, which is this curve here. And what we can do is let's practice evaluating this training loss at a particular value of w, let's say 1. So this is going to take the average over this data set, and it's going to return some value, 7.5. Okay, so the loss of the average loss at w equals 1 is 7.5. So, which seems okay, but now let's peer a little bit closer at how the loss is spread across groups. Okay, so we're going to define a notion of a per group loss. So here's our training set. So for group A, what is this loss? And group B, what's this loss? So formally, we're going to define the per group loss, written train loss sub G for group G. G can be either A or B, to be the average now over only those examples in that group. So this notation, D train of G, is the set of examples in group G, and of the per example loss again. Okay, so we're going to plot these two losses on this curve here. And we see that we have these two plots. So train loss A looks like this, and train loss B looks like that. And we can practice evaluating these different loss functions at our example weight vector 1 here. So train loss A is going to be an average, remember, only over the examples in group A. And that's going to give us 22.5. You can see it looks like about 22.5 here. And then what about B? So B actually gets a loss of 0, which you can see at this point. So you can see that we have a single weight vector 1 gets very different losses on the two data sets, on the two groups. A is doing a lot worse, it has 22.5, and B is doing much better. It has a 0, which is the minimum loss you can hope for. So this is an example of a disparity between, if we were to choose weight vector 1, there would be a huge disparity between the performance on these two groups. So, so we can look at the losses of different groups, but it'll be helpful to kind of summarize that as a single number. And we're going to capture it by a quantity called the maximum group loss. And you might guess from the name that the maximum group loss, written train loss max, is simply just going to be the maximum over all groups of the per group loss. And so visually what this looks like is as follows. So let me, so remember we had in yellow here, or orange, the loss of group A, and in blue we have the loss of group B, and the maximum group loss is this function of W as the other functions, which is going to be the point-wise maximum. So at every point we choose either the value of that's loss of A or B that's going to be larger. So as you can see, it traces out in kind of upper envelope here. Over here, it's the loss of A is higher, so it's going to track that. And over here, the loss of B is higher, so it kind of hugs B from there on. Okay, so let's evaluate at our point W equals 1. We see that, remember from the previous slide, that the two losses are 22.5 and 0 for the two groups. And then to compute the maximum, we just take the max of these two values and you get 22.5. So 22.5 is a single number that summarizes how bad is the worst group off? And what's the maximum group loss? And if you compare the maximum group loss, 22.5, with the average loss, which is 7.5, you see that the maximum group loss is larger, and it's always larger. So now let's compare these two loss functions. So we have the average loss and the maximum group loss. So we can plot both of these here. And pictorially we can see what's going on. So here, let me just plot our data points just so we have them available. So these functions are definitely very different. Okay, so what happens now when we try to minimize the average loss versus the maximum group loss? So let's start with minimizing the average loss. So this is standard learning. It says a status quo. You find the minimum of the average loss, which is going to be this point, W equals 1.09. It gets a loss of 7.29. So it looks like we were doing pretty well, but if you remember, look at the worst group loss of that weight vector, then we'll see that it's above 20, which is not great. So what you can do instead is to do what we call group distributionally robust optimization, or group DRO, which is simply going to minimize the maximum group loss. So it's going to minimize this purple plot here. And what happens when you do that, you get W equals 1.58, which gets a loss of 15.69, which is better than the 20 plus that you would have gone there. Now, of course, the average loss is worsened because at this point, the average loss on the red curve is a little bit higher. So there's a trade-off here. And we can see this tension kind of play out over on this plot over here. So here we see that if you were to minimize the average loss, what you would do is find a regressor or a model that's very close to the points over here, B, because there's 4 of them. It kind of the majority class dominates. Whereas if you minimize the maximum group loss, then you're going to get this purple line, which is going to be able to balance out the two groups, no matter how many points are over here versus over here. So you can think about this, the purple line is more fair because it treats groups more equally. So how do we minimize the maximum group loss? So as before, we're going to use gradient descent and follow our nose. So what this looks like, let me just try to plot this. So here's the objective function. The maximum group loss is train loss of max is, remember, the maximum over all the groups of the per group training loss. And so how do you take the gradient of a max? Well, the gradient of a max, remember, is equal to the gradient of the function where we're evaluating at the particular value of g star. And what is g star? G star is the argmax over the training loss. So let's look at this picture. So basically what we're doing, so we want to take the gradient of this purple curve, right? And so if you're over here, the gradient of the purple curve is exactly the gradient of the loss on group A. And if you're over here, the gradient of the maximum group loss is exactly the gradient of group B. And it's exactly corresponds to G star is A over here because group A is worse, and G star is B over here because group B is worse. So to compute the gradient, it's actually kind of very simple. You first just evaluate at your current weight vector, what are the losses of the different groups? And you look at the group that is hurting the most, has the highest loss, and then you just update on those examples. So it's a very intuitive process. You find which group needs the most amount of help, and then you only update your parameters based on that group. So one note is that it's important that we're talking about gradient descent. not stochastic gradient descent. Because stochastic gradient descent relies on the objective function being a sum over terms. But this is a maximum over a sum. So it exactly won't work. How to exactly get stochastic methods to work properly is beyond the scope of this module, but you can read the notes for pointers. Okay, so let me summarize here. So we've introduced the setting where examples are associated with groups. We've done it for group regression, but this generalizes for classification and other more general machine learning problems. We saw that we have the average loss and the maximum group loss, and these are different. What is good on average is not going to be a group for all groups. And we see that there's always a tension between the groups if the groups are pulling you in kind of different directions. And we saw that group distributionally robust optimization, or group DRO, is a very simple algorithm that minimizes the maximum group loss, the purple curve over here. And finally, I want to remark that this module has kept things simple, but there's many, many more nuances. So intersectionality is this principle or property where a group such as white women is actually made out of multiple attributes, and these groups might behave differently than the more coarse groups, the women or the set of white people. And so we have to kind of take into account finer grained groups. There are also cases where we might not know what the groups are. Maybe we don't collect demographic information and we have to infer them. There's also an issue with overfitting. We're talking only about the training loss here, just for simplicity. But of course, what we care about in machine learning is doing well on out of a test set. But we're not talking about a test set here. So there's many more references in the notes. And I hope this has piqued your interest, and realizing that inequality should be considered a first-class citizen when we think about machine learning methods. So that's it. Thank you.